Now we take another concept, the apparent weight of a body in a lift. When you are standing on a weighing machine, what weighing machine shows? The reading of your weight. You know what is that unit? Yes, it is kg weight. When you are standing on weighing machine, your weight is acting vertically down. This is the action on the floor of the weighing machine, and the normal reaction due to this flow is acting vertically up. This is the normal reaction. At equilibrium, when weighing machine is stationary, R equal to mg, that is upward forces is equal to downward forces. That means whatever the normal reaction, that is readed as weight. The normal reaction is readed as weight. When this weighing machine is stationary, the weight is nothing but mg. This is true weight. Suppose we consider this weighing machine is placed in a lift. If the lift is stationary, simply we can write R equal to mg. The weight recorded on the weighing machine is the true weight of the body. If we consider when the lift is moving up with acceleration a, what are the different forces acting on the body? Mg is vertically down, R is the normal reaction due to surface of the lift. This is opposite to mg, and a is vertically up. In this case we can write m into a, this is equal to R minus mg, or R equal to mg plus ma. Already I told the weight is nothing but the normal reaction. In this case, the normal reaction is more compared to your weight. The weight appears to be increased when the lift is moving up. This is the apparent weight. That means when lift is moving up with acceleration a, the apparent weight is more than the true weight. In this case, the apparent weight W prime, this is equal to mg plus ma. This is nothing but W into 1 plus a by g, where W equal to mg is the true weight. Now we consider the lift is moving down with acceleration a. In this case, the different forces acting on the body are the weight of the body, mg is acting vertically down, the normal reaction, R is vertically up, and ma, this is down. The net force ma equal to mg minus R, or R equal to mg minus ma. That means the normal reaction is less than the weight, or the apparent weight is less than true weight. The apparent weight W prime equal to W into 1 minus a by g. That means when the lift is moving down, the weight of the body appears to be decreased. Is it really decreasing or increasing? Just it appears. This is just a magic of motion. It's not really increasing or decreasing. Suppose in the same problem, if I consider the lift is falling freely. A lift is falling freely. One lift can fall freely. Yes, if you cut this string, then it falls freely. In this case, A equal to G, then W prime equal to W into 1 minus G by G. This is equal to 0. That means the apparent weight of a freely falling body is 0. When lift is moving with constant velocity, what is acceleration? Acceleration is 0. In that case, W prime equal to W, A equal to 0, and apparent weight W prime equal to W. Now we take another concept, equilibrium. When a body is said to be at equilibrium, when the net force acting on the body is 0, then we can say the body is at equilibrium. Suppose if I consider an object of mass m placed on an horizontal surface. In this case, the weight is mg acting vertically down, the normal reaction n is vertically up. I am considering the body is at rest. It is in equilibrium. Does it mean no force is acting on the body? Yes, two forces are acting on the body, but the net force acting on the body is 0. This type of status is called equilibrium. Similarly, if I consider a mass m is suspended with a string, this is at equilibrium when it is stationary. In this case, the weight of the body mg is acting vertically down and the tension developed is along this direction. Here also, two forces are acting on the body, but the net force on the body is 0. And you take another example. on a horizontal surface, a mass m is placed, a force F is applied along this direction, another force F is applied along this direction. What is the resultant force? 0. Here also we can say the body is at equilibrium. And we take another problem. On this mass, two forces F1 and F2 are acting along this direction. The resultant of these two forces is along this direction. The body will move along this direction. Suppose I want to keep this body in equilibrium. Then what I have to do? If I apply a force F3 exactly opposite to this, equal in magnitude, which is equal to F, then the body is in equilibrium. In this case, three different forces are acting on the body. The body is at equilibrium. That means the net force acting on the body is 0. And one more important thing, these three forces F1, F2, F3, these three can represent as the adjacent sides of a triangle. This is F1, F2 and F3. The starting point of F1 and ending point of F3 are same. Hence, the resultant force is 0. This is the triangle law of forces. That means if three forces acting on a body can represent the adjacent sides of a triangle, then the resultant of these three forces is equal to 0. From the same thing, we can develop a Lamy's theorem. According to Lamy's theorem, if three forces F1, F2, F3 are acting on a body so that the angle between F1 and F2 is gamma, F2 and F3 is alpha, F1 and F3 is beta, then we can write F1 by sine alpha, this is equal to F2 by sine beta, this is equal to F3 by sine gamma. This is Lamy's theorem. This is applicable when the body is in equilibrium. Now we take another model. A mass m is attached to two strings, as I was saying in the figure. The weight mg is vertically down. If this is in equilibrium, what you can say? Yes, the resultant of T1 and T2 is equal to mg. If mg is more, then automatically the body will fall down. In this case, mg is the resultant of T1 and T2, and this is equal to root of T1 square plus T2 square plus T1 T2 cos theta from parallelogram law of vector addition. Now we take another problem. In above problem, if this T1 is making an angle theta 1 with the horizontal and this is making an angle theta 2 with the horizontal, then this T1 can be divided into two components, T1 cos theta 1 and T1 sin theta 1. This is horizontal component and this is vertical component, and T2 also can be divided into two components, T2 cos theta 2 and T2 sin theta 2. At equilibrium we can write T1 sin theta 1 plus T2 sin theta 2, this is equal to m into g. Now we take another problem. Suppose we consider a mass 10 kg is suspended due to two strings T1 and T2 to a rigid support, as I was seeing in the figure. The strings are making angles 30 degrees and 60 degrees with horizontal surface, and this is angle 90 degrees. Now from this problem, we have to calculate the values of T1 and T2. Now this is mass 10 kg. The system is in equilibrium. This T1, the tension along the string, this can be divided into two components. Before that, this angle is 30 degrees, this angle is 30 degrees, these two are alternative angles. This T1 can be divided into two components. One is T1 cos 30, another is T1 sin 30. If this is 60 degrees, this angle is 60 degrees, these two are alternative angles. And T2 can be divided into two components, T2 cos 60 and T2 sin 60. Now from this figure, we can write T1 cos 30, this is equal to T2 cos 60 at equilibrium, or cos 30 is root 3 by 2, cos 60 is 1 by 2. Therefore, root 3 T1 equal to T2. At equilibrium, the forces in vertical direction equal to the forces in downward direction. The vertical forces are T1 sin 30 plus T2 sin 60. Now this is equal to 10 kg weight. This is the downward force. T1 into 1 by 2, sin 30 is 1 by 2, and T2 is root 3 T1 plus root 3 T1 into root 3 by 2, that is sin 60. This is equal to 10. From this we get 2t1 is 10 and t1 equal to 5 kg weight and t2 equal to root 3 into 5, root 3 into t1, that is root 3 into 5, 5 root 3 kg weight. 1 kg weight is 1 into the value of acceleration due to gravity g, that is 9.8 Newton. These are some models related to equilibrium.